Chemical engineering is the application of principles of chemistry, physics, and engineering to convert materials into something else. Chemical engineers can have a multitude of responsibilities, such as managing a chemical plant, designing a chemical manufacturing process, quality assurance, maintaining lab safety, optimizing reactor design, and much more. Above all else, a chemical engineer uses their knowledge to solve problems in innovative ways. Common places where you can find chemical engineers are oil refineries, pharmaceutical plants, wastewater treatment facilities, defense companies, academia, and even other fields such as finance. Another important industry for chemical engineers is polymers.
Polymers are large chains of repeating units. These units are known as monomers. They are essential to our daily life. They can be found in things such as building materials, adhesives, and plastics. In this lab, we will be polymerizing methyl methacrylate, our monomer, to form polymethyl methacrylate. We will be using free radical polymerization to form our polymer. Free radicals are unpaired electrons, which are highly reactive and dangerous. Free radical polymerization has 3 steps: initiation, propagation, and termination. During initiation, the initiator will contain at least 1 unpaired electron. The radical will attack the monomer, moving its free radical onto the methyl methacrylate. From here, propagation occurs, and this free radical will continually attack monomers, adding to the chain. As long as there is a monomer available, this chain will continue growing. To stop polymerization, the final step, termination, begins. In this stage, the free radical will be stopped. To do so, the polymer chains will either combine through forming a stable bond, and the chain will form even longer, or the free radical will be moved to a new chain in the form of a hydrogen atom, ending the growth of the 2 chains. Our goals for this lab are twofold. Firstly, we were tasked to determine the accuracy of the thermal coupler, which is how we measure the temperature during our experiment. And secondly, we will be determining the activation energy for the polymerization reaction. Activation energy is a very important reaction parameter to know. If you're sitting on the couch thinking about having to go clean your room, the activation energy would be getting up and going to your room. Once you start the process, it's easy to keep going. Activation energy is a number that represents getting up off the couch for a reaction and is dependent on the temperature.
To determine the validity of the thermocoupler, we boiled a beaker of purified water and measured the temperature with the thermocoupler. Since we know water will boil at 100 degrees Celsius, it is off by about 2 degrees. Let's take a look at what equipment we will be using for the polymerization reaction. Here you can see the dilatometer. It is a U-shaped glass tube with a small chamber where the polymerization reaction takes place. This is the cathetometer. This is sort of like a telescope and a ruler mixed into one. You look through the little porthole to line up the crosshairs with the meniscus of the liquid in the dilatometer. It can then be adjusted to a different height.
Now let's perform the experiment. Once the monomer solution is prepared, we put it into the dilatometer. We then place the dilatometer into the silicone oil bath to kick off the initiation phase of the reaction. Then we use the cathetometer to measure extent of reaction. Since polymers are more dense than monomers, the height of the liquid will go down as more polymers are formed. We can use this change in height to find the change in volume, which can then be linked to the density and the extent of reaction via equations. For these trials, we start the cathetometer at 40 centimeters, and when the meniscus reaches the point of the crosshair, we start a timer. We then lower the cathetometer 1 centimeter at a time and take the time and temperature at each point. We perform this experiment at 2 different temperatures so that we can compare the change in rates of reaction. Once the cathetometer reaches 20 centimeters, we stop the reaction and we clean up. Now let's take a look at the polymer that we created. First, we have to extract our liquid polymer from the solution, cool it in an ice bath, and cause it to precipitate out by adding additional solvent. Here you see the final product.
It is important to dispose of your hazardous waste properly. This includes properly labeling all waste as well as being sure not to mix waste chemicals that can react. Also, during the lab, it is important to be aware of the specifics, hazardous of the chemicals you are working with, and wear the appropriate PPE.
Now we take the data from our experiments and put it in Excel. Here we can calculate the activation energy and visualize our data. This information would help a polymer manufacturer design a reactor for the production of polymethyl methacrylate and would aid in predicting the energy cost.